And next on stage is Sumathi R.Radhakrishnan from Berlin's very own Institute for Crystal Growth. Welcome on stage.
First of all, I thank Oliver and Asa for inviting me to give a talk here, and I'm very glad to give a talk in this workshop on emerging materials for future of computing. And I am Radhakrishnan Sumathi from Leibniz-Institut for Crystal Growth in Berlin. It's very close, in Adlershof. And today I would like to show you some of our bulk single crystals, how they are going to be useful for quantum computing applications. Okay, I would like to follow this outline for the next 10 minutes, and I will give a very short overview about our institute, and then I will focus mainly on three different single crystalline materials: silicon, germanium, and germanium-silicon-based alloy systems, how they are useful for quantum computing or making qubits, and how we prepare these materials. That is also important. And finally, some messages to take away. Sorry. Yes, before going to the topic of quantum computing, I would like to introduce our institute. It is a Leibniz-Institut for Crystal Growth, and we are around 150 employees working in this institute and 55 scientists, equally supported by the technical and administrative staffs. And we have a lot of PhD students as well to work on different topics of crystal growth and based related research. And this, as I mentioned, this is a Leibniz Institute. I did not see our institute in the list of Jens, Professor Jens, which he showed a map. Since we are also in Adlershof, very close to Helmholtz-Zentrum, Berlin, and so maybe in future we will have our institute as well in this diagram. Yes. Okay, first I would like to start with the silicon. Yeah, silicon, you know, it's a very well-known material for it is in the whole computing era. And what is the advantage of silicon for using quantum computing or any of the devices fabricated on silicon is the scalability. Yeah? So this is a very important property of this material, and there are a variety of possibilities to make qubits on silicon where we collaborate with the different groups worldwide, for example, University of New South Wales, and also some of the groups which are Kobayashi from the same group, and also from Helmholtz-Zentrum Dresden. And what they do is, because we are only the producers of the materials and we don't do the quantum devices by ourselves, but our collaborators, what they do is, there is a possibility to do the donor qubits on silicon or the whole spin qubits. The donor qubits, you can do it by implanting phosphorus, as Peter told. You can make an ion implantation in the material, and these phosphorus donors act as in silicon, and also isotopically purified silicon-28. You know, the isotopically enriched material give very high efficiency for your qubits, and also very long coherence time for your qubits. And the other possibility is to dope boron in silicon or in silicon-28 enriched material, so that these holes which are bound to the boron acceptors, they causes a very high decoherence, so that you will have a very long coherence time in the qubit. So this is how the device was fabricated, and the boron is doped in isotopically enriched silicon-28, and this was thinned down to 50 micrometer slice, and this was attached to a fused silica, so that it is bonded to fused silica, so that you can create a strain in the layer. So the strain is very important to make a very high mobility in the devices. So I would like to point out here that our institute has supplied this isotopically enriched material to the substrates in the form of substrates, and also in the form of targets for the MBE layers, to grow the MBE layers for the several groups in the worldwide. Yes. So the silicon, there is another application of silicon is to make quantum emitters. This is a single photon emission from silicon-28 or the natural silicon that can be created by color centers. As Peter told in the nitrogen vacancy in diamond, likewise you can create a lot of color centers in silicon based on different defect creation. For example, you can create a T center by a pair of carbon atoms, and one of the carbon atom bonded to hydrogen, and the another one is free with the free electron. Or you can create a W center, which is only made of defects, not impurities. It is only the 3 interstitial silicon which are bonded to each other. Or you can create G center, which is again carbon atoms, but it is bonded to one of the silicon atom. And so such color centers are mainly useful for emitting single photon emission, and they emit particularly in the direct wavelength, which is related to the telecommunication wavelength. Yeah, so this is a wavelength region. So it's a very interesting and efficient quantum emitters and quantum memories can be fabricated using this material. And now I would like to come back to what we are doing at our institute to supply this material is we are growing bulk crystals of silicon and silicon-28 using floating zone technique. This is one of the crystal, and this is 4-inch diameter isotopically pure silicon-28 single crystal, which has been grown for Avogadro project, which is a historical project of our institute to prepare a 1 kilogram ball to redefine the kilogram unit. So this is how the history of isotopic material started in our institute, and still we are working on this material for the applications of quantum computing. But yeah, this isotopic material is enriched in Russia, and so all these process steps should be done before getting the isotopic material, starting from silicon tetrafluoride and then doing the CVD to get the polycrystalline rod for growing the single crystal, and then do the floating zone crystal. So these floating zone crystals, we can purify chemically as well, up to very high purity. And you can see here that the concentration of impurities are in the order of 10 power 14 or to the 10 to the power 15 per cubic centimeter. And the oxygen and carbon are the main impurities. They are very well under 10 power 15. And this is very important for people who want to fabricate a device. So the next material is germanium. Germanium is also a very interesting material. It can replace, it is a natural choice to replace silicon in some of the aspects. And because the germanium-based qubits are mainly based on whole spin qubits, this is what is interesting in germanium. And also, it is the material, it is the only material that can be purified up to very high purity, ultra high level purity, and such an high purity, plus when we are doping this material to very low concentration. For example, if you're reaching the very high purity into the order of a net charge carrier concentration 10 to the 10, and if you're doping this material 2 orders higher, 10 to the 12, it's a very low doping, then you can put your atoms, impurity atoms, in a place so that they can act as qubits, or you can manipulate them to make emission from these ions or atoms so that you can get a single photon emission in these devices. And so there are a lot of possible ways how you can do this doping. Is you can diffuse the atom, or you can do the ion implantation, or the neutron transmutation doping in isotopic materials. So these are the possible ways, and this way you can easily study the properties of the material for quantum applications. And also, germanium can be used as a substrate for fabricating heterostructures of silicon germanium layers, where you can produce the strained germanium layer for quantum device. So there are a lot of applications for the bulk germanium crystals. I'm mainly focusing on bulk materials. And and also sometimes epitaxial layers. So how we can get a highly pure germanium? This is our challenging task at our institute, and there are a lot of process steps involved in this, because we have to start from very unpure germanium dioxide powder. It is only 4N pure, and we have to reduce it to a germanium metal, and then to zone refine this metal up to a high purity, up to 13N purity. This is the highest purity one can achieve in germanium. And then after this purified material, we go to the crystal growth. The crystal growth is being done in the conventional Sokolsky growth of how the silicon and germanium crystals are being grown. And such high purity germanium can be used for two different applications. The main application for germanium right now is high purity germanium detectors. It's a radiation detection. And our aim is to also use this material for quantum communication things. And these are some of the properties of the materials, and the important property which I would like to mention here is the net charge carrier concentration. It is the impurity, background impurity concentration is very, very low, in the order of 10 power 10 at liquid nitrogen temperature, and the mobility is very high. Because at room temperature, germanium is intrinsic, and so we have to always talk about the liquid nitrogen temperature properties for germanium. And also we have a very unique technique which is called a photothermal ionization spectroscopy to identify what type of impurities are in our material and how we can estimate the concentration of them together with the Hall effect measurement. And also the defect density is very low, in the order of thousands. It is very, very low when compared to the epitaxial layers, and so these crystals will be very useful to be used as substrates for devices. And the last material I would like to focus is the germanium silicon. It's not an epi layer, it is a bulk crystal I want to mention. And usually this is in discussion together with IBM. And in IBM, we have been in a meeting, and they are using such type of heterostructures to make quantum devices. And in that case, the strained 76 germanium layer should be produced on such a stack of epitaxial layers. So here what you see is the virtual substrate of silicon germanium alloy system, and this has been grown on silicon. So there are a very big lattice mismatch between silicon germanium and silicon, and so this creates a lot of dislocation in the epi layers, and this is a problem for the devices. For example, if you have a compositional fluctuations, then this will also affect the strain in the germanium 76 layer, the fluctuation of the strain. So one of the possible option is to go for the bulk substrates of germanium silicon to replace this virtual substrate. So the bulk crystals always, most of the time, they have very low dislocation density. It is 3 orders or 4 orders lower than the epitaxial layers. So if we replace these virtual substrates by bulk silicon germanium, then we can get a very good device structures without with very high efficiency. And this is what we are currently doing, and we are developing bulk crystals of germanium silicon up to 20% of silicon in germanium. So this is currently being done, so I could not present some of the results from here, but it is possible to do it. And so as a summary or some takeaway message, what I can say is that in our institute, we are growing isotopically pure as well as natural bulk crystals, which can be used for quantum computing applications. Also, we have a small epitaxial group who are growing MBE layers of isotopical materials. And if some of you are interested, then we can also discuss about it. And yes, ultra-high pure materials are very hot major topic of our group. We are looking for some cooperation because we produce materials, and if there are some people interested in using our material, then we will be very happy about it. And so with this, I would like to thank you all for your kind attention, and I thank all my team members and the funding agencies and collaborators. Thank you very much.
Thank you, Sumathi.